Alright, in this video we study the determinant of a general n by n matrix, but its definition is quite complicated. So we first give the definition mechanically, and also that is recursive, and then after that we think about its meaning. Okay, let's start. Okay, so here's the definition of the determinant of general n by n matrix. So let A be a matrix whose elements are aij and the size is n by n. Okay, and the determinant of A. So the determinant is defined as follows. If n is equal to 1, then the determinant is just a11, so it's sole element. Okay, and if n is greater than 1, then the determinant is given by the following recursive formula. Okay, let aij, so this is capital Aij, so don't confuse this with the element aij, but it's okay, we define this capital Aij as another matrix that is n minus 1 by n minus 1 square matrix. That is obtained by removing the ith row and jth column of matrix A. Okay, so if we have a square matrix, then that is A, and this Aij is obtained by removing the ith row and the jth column. So ith row and jth column. So the remaining part, by connecting the remaining part, this part and this part and this part and this part, we can construct another a little bit smaller matrix. So that is called Aij. Okay. Then the determinant of A is given by this. So J runs from I to N and -1 to the power of I plus J. And here I is any number from any natural number from I to N. That points to the ith row of matrix A, and Aij, so this is the ij element of the matrix A, and times the determinant of this matrix uppercase Aij. Okay, so this is the definition. So what this means is that when we calculate this determinant, we need to know the determinant of smaller matrices, Aij. So this I and J, so I is fixed here, and J runs from 1 to n. So we need to determine the determinants of n such smaller matrices. But in order to calculate these determinants, then we apply the same formula again, but for this smaller matrix. Okay. So to do that, we need the determinants of even smaller matrices, right? So that will be the matrices of the size of n minus 2 by n minus 2. And we continue this over and over until we reach n equal to 1. So for that case, we know how to calculate that. Okay. Actually, this definition is usually derived as a theorem in the ordinary linear algebra course, but the standard definition of determinant is too complicated and beyond the scope of this lecture. So we just accept this as a definition. Okay, but it required some examination to see that if we can really choose any I to determine this determinant. Okay, so what this says is that whatever the choice of this I is, so I can be any natural number from 1 to n, we still have the same value. Okay, and we don't prove this exactly, but you should try to calculate some concrete determinants by using different values of I, and we'll see that later. Maybe this definition is too abstract, so let's consider concrete examples. First, let's consider the determinant of 2 by 2 matrix, let's say A, B, C, D. And in a previous video, we already defined the determinant of this matrix, 2 by 2 matrix. And we know that this is this A times D minus B times C. So A, D minus B, C. Okay, so we already know this. But let's apply this definition to calculate the determinant of this and see if it is really equal to this one. Okay, so A, B, C, D, it's matrix. Okay, for this example, let's pick I equal to 1. Okay, so that is this, the first row. And in that case, let's say J is equal to 1. So in that case, we have negative 1, I is 1, and J runs from 1 to 2. Okay, so the first term is 1. Okay, and Aij here, in this case, first we take one element, so that is A here. And the determinant is the determinant of the smaller matrix is this part. Okay, so we remove the ith row, in this case the first row, and we here J is 1, so we remove the first column. So the remaining part is only this element. So that is the matrix made of only D. Okay, so this is the first term. And the next term, J is equal to 2. Okay, I is still 1, fixed to 1, and J is 2. And the 1, 2 element is B. So that is B. And if we remove the first row and the second column, what remains is this, C. Okay, so we calculate the determinant of this 1 by 1 matrix made of only C. Now we know how to calculate this according to the first case here. So that is just that element here. Okay, so negative 1 to the power of 2 is 1, so A, and this is D, right? So, and plus negative 1 to the power of 3 is negative 1. And this is B times this is C. Okay, so the result is AD minus BC, which matches the result of the previous definition. Now in this definition, we said this I here, this index I can be chosen arbitrarily from 1 to n. So let's calculate the same thing again, but using different I. Okay. So A, B, C, D, and this time let's pick the second row. Okay, so this would be I would be 2, right? I is 2, second row, and negative 1, 2 plus. Let's pick J is equal to 1, and 2, 1 element is C. Okay. And if we remove the second row and the first column, the remaining matrix is made of B. And negative 1 to the power of 2 plus 2, second row, and the second column. And 2, 2 element is D. And the smaller matrix is made of, so remove the second row and the second column, the remaining matrix is made of A. So this is, so negative 1 to the power of 3 is negative C, B, plus This is positive 1. And D, A. So this is again, we have AD minus BC, same result. Actually, this definition also applies if we swap the roles of the row and the column. Okay, so instead of summing over the index of the column index, we can sum over row index and fix some index of the column. Okay, that means instead of picking a row arbitrarily, we can pick a column arbitrarily. Okay, but still the same approach definition applies. So let's do that. So A, B, C, D. So instead of picking a row, let's pick a column. Let's pick this column. So J is fixed to 1. And the index I, the row index, runs from 1 to 2. Okay, so negative 1, and I is 1, and J is 1. And this element is A. Okay, the smaller matrix in this case is D. D. And next, instead of picking the next element in the same row, we pick the next element in the same column. Okay, so C, and here I is 2 and J is fixed to 1, and this C, and the remaining matrix is this B. Right? So this part is positive 1 times A times D, and this one is negative 1 and B times C. So again, we have AD minus BC, the same result. And also, of course, you can pick the second column instead of the first column. Okay, let's do that again. Maybe you get tired here, but let's check it. So we pick this column, and negative 1 to the power of first row and the second column. So first row and the second column. And the element is B, and the remaining element is C. So smaller matrix is made of only C, and negative 1, and this 2 element, 2 element, and D, and the smaller matrix is made of A. Okay, again we have negative BC here and positive AD here. So again and again we get the same result. Okay, next let's consider this 3 by 3 matrix. Okay, made of 1, 0, 2, negative 1, 1, 1, 0, 1, 0. Okay, let's calculate the determinant of this. First, let's pick the first row. Okay, so negative 1 and 1 plus 1. 1 element is 1. Oops, this one. So that's 1. And the smaller matrix in this case is this part. Okay, remove the first row and the first column. The remaining matrix is made of 1, 1, 1, 0. Okay, next pick this element, 1, 2 element. So negative 1 and 1, 2 element, which is 0. But since we multiply by 0, whatever the remaining matrix is, it doesn't matter. So let's ignore that. And next one, 1, 3 element, negative 1 to the power of 1, 3. And the element is 2. And the remaining matrix is this one. Okay, negative 1, 1, 0, 1. Okay, and now we know how to calculate the determinants of 2 by 2 matrices, right? So for this part, we get 1 and 1, and this matrix, the determinant is 1 times 0 minus 1 times 1, so that's negative 1. And the next one, 1 to the power of negative 1 to the power of 3 is negative 1, but this is 0. So it's just 0, it just disappears. And the last term is 1 to a negative 1 to the power of 4 is 1 and 2. And this determinant, negative 1 times 1 minus 0 times 1, that's negative 1. Okay, so that's negative 1 and that's negative 2, and the result is negative 3. But if you observe this matrix more carefully, uh, we said you can pick any row or column to get the same result, right? So you should pick the row or the column that makes the calculation the easiest. Okay, in that case, that would be this row. Okay, because we have 2 zeros here. Only non-zero element in this row is this one. Okay, so the smaller matrices for this first element corresponding to the first element in this third element, they will just disappear because it's 0, right? So the only thing that matters is this one, the middle one, and the remaining matrix that is made of this and this part. Okay, so let's do that. So just ignore this part and pick this one. So negative 1 to the power of, that is 2 element, right? Third row and the second column. That's third row and second column. And that element is 1. And the smaller matrix in this case is 1, negative 1, and 2, and 1. 1, negative, and 2, 1. So this is negative 1, and 1, and 1, and wait a minute. 2, yeah, 3 plus 2, okay. And 1 times 1 minus 2, negative 1, times 2. So that's positive 3. And the result is negative 3. So this is a little bit easier than the previous way of calculating the same thing. Okay, next let's consider calculating the determinant of a general 3 by 3 matrix. So that is x, x11, x12, x13, x21, x22, x23, x31, x32, x33. So let's calculate the determinant of this matrix and just apply the definition here. Let's pick this first row, negative 1 plus 1 plus 1, x11, and the determinant of the remaining part, x22, x23, x32, x33, and negative 1, this one, so that's 1, 2 element. And the remaining part is this and this. So the determinant is, x21, x23, x31, and x33. And the next one, let's pick this one. That's 1, 3 element. And the remaining matrix is, the smaller one is this one, x21, x22, x31, x32. Okay, then just expand, and this is 1, x11, and x22, x33, minus x23, x32, and negative x12, and x21, x33, minus x23, x31, and plus x13, x21, x21, x32, minus x22, x31. So let's expand this this and this and this and this and this and this and so on. So we have x11, x22, x33, and minus x11, x23, x32, and minus x12, x21, x33, and x12, x23, x31, and x13, x21, x32, and x13, x22, x31. Okay, so in total there are 1, 2, 3, 4, 5, 6 terms. So what are these 6 terms? Okay, let's look at these indices, right? So the row index is 1 and the column index is 1 here, and 2, 2, and 3, 3. And here 1, 2, 3, and 1, 3, 2. Here we have 1, 2, 3 for the rows, and 2, 1, 3 for the columns. And 1, 2, 3 for the rows, and 2, 3, 1 for the columns. 1, 2, 3 for the rows, and 3, 1, 2 for the columns. 1, 2, 3, and 3, 2, 1. So these are actually permutations of 3 numbers. Okay, if you permutate 1, 2, 3, so the number of possible ordering of these 3 numbers is 3 factorial, that is 6. So the row indices are ordered here in this order. It's always 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, right? In all these terms, it's ordered in the order of 1, 2, 3. But the column indices here corresponds to the possible permutations of these numbers. So it can be just no permutation, 1, 2, 3. It can be just swap the last 2 numbers, 2 and 3, and 1 remains the same. Okay, if you consider these permutations, you get 6 possibilities. And what about the signs here? Signs. We have sometimes negative and wait a minute, this should be positive. Okay, sometimes negative and sometimes positive. So what are the differences? Okay, so any permutation can be achieved by swapping 2 numbers multiple times, possibly 1 time or multiple times. So if you can obtain 1 permutation by swapping 2 numbers odd number of times, then the sign is negative. If you can obtain the permutation by swapping 2 numbers even number of times, then the sign is positive. Let's see here. So 1, 2, 3, 1, 2, 3. So this is permutation. This permutation can be obtained by swapping 0 number of times, right? So this is even. And here, let's consider this one. 1, 2, 3 becomes 1, 3, 2. So we swap these 2 numbers once. So this is odd number of times. So that is negative. Okay, and let's consider this one. 1, 2, 3 becomes 2, 1, 3. 2, 1, 3. So this can be obtained by swapping 1 and 2 only once. So that is odd number, and we have negative sign here. What about this one? 1, 2, 3 becomes 1, 2, 3 becomes 2, 3, 1. 2, 3, 1. So how can we obtain this permutation by swapping 2 numbers multiple times? So let's try that. So 1, 2, 3. Let's swap 3 and 1 first. 3 and 1. And next swap 3 and 2 here. This one. Then we get 2, 3, 1. So that is this one. Right? So we swapped twice. That is even number. and we have this positive sign. And the next one, 1, 2, 3 becomes 3, 1, 2. 1, 2, 3 becomes 3, 1, 2. So how can we obtain this? So 1, 2, 3. Let's swap. Let's see. 3 and 1. And next, let's swap 2 and 1. Okay, 3 and 1, and 2 and 1. 3, 1, 2. So that's it. So we swapped 2 times. That's even number, and we have the positive sign. Well, 3, 3, 1, 2. Which one was it? 3, 1, 2. Oh, this one. Okay, positive sign. And this one, 3, 2, 1. So 3, 2, 1. 1, 2, 3. This can be obtained by swapping 3 and 1 only once. Okay, so that's odd number, and we have this negative sign. So odd number of times, negative sign, and even number of times, positive sign. That's the pattern here. And actually, this pattern applies to any dimensions. Okay, so if we have n by n matrix, then we have terms like x1, let's say I1, x2, I2, and so on, xn, in. So this I1, I2, in, so 3 and so on. These are actually permutations of these numbers, n numbers, I1, I2, I3, and so on, in. And if this permutation can be achieved by swapping pairs of numbers, odd number of times, then the sign will become negative. And that if the same can be achieved by even number of times, the sign becomes positive. And we consider all possible permutations. So in case of n by n matrix, there will be n factorial number of terms in the determinant. So you may want to examine this pattern for a general 4x4 matrix. And I don't do that here, but you should try that. Okay, that's all for this video. In the next video, we study some of the important properties of determinants in general. Okay, see you later.